Hi guys, this is video 7 in the series of ship stability, and today we'll be talking about the center of buoyancy, which is denoted by the capital letter B or the acronym COB. So in the previous videos we've been talking about all the center of gravity, and I'll provide you with the link of that video as well. But today's video is focusing only on the center of buoyancy, denoted by B or COB, where COB stands for center of buoyancy. Alright, so this is video 7 of the ship stability series. I will provide you with the links of all the previous 6 videos in the description section of this video. So let's start before I waste any more of your time here. So what is the center of buoyancy? So the center of buoyancy of a ship is that point through which the force of buoyancy may be considered to act vertically upwards with a force equal to the weight of water displaced by the ship. Alright, so that's basically helps in the flotation of the ship. So as you know that the center of gravity of the ship pulls the weight of the ship downwards, right? Because the gravity pulls us downwards. So we need an equal and opposing force to keep the ship afloat, otherwise the ships will sink. So ships are heavy, huge, massive objects, right? If you take an iron ball and try to put it on the water, the ball will sink because this force of gravity is much stronger than the force of buoyancy. But if you take a paper, or not a paper rather, but a piece of wood and try to float it on the water, you will realize that it floats on the water because the force of buoyancy is more, or it's equal and opposing to the force of gravity. Alright, so that's the same case with the ship as well. So this force acts vertically upwards and helps to counteract the force of gravity to keep the ship afloat. Now the center of buoyancy, it is the geometric center of the water displaced. I'll show you what I mean by the geometric center when I discuss the figure below, or the geometric center of the underwater volume of the ship. So when a ship is floating in the water, part of it is submerged in the water. So that part, or the volume of that part of the ship, is the underwater volume, and the geometric center of that underwater volume is the center of buoyancy of that ship. Alright, so the position of the center of buoyancy is indicated by 3 indicators. The first indicator is this height above the keel. The height above the keel is referred to as KB, alright, where K is the keel. So you can see here in the figure, this figure here, K is the center or the keel. K is in the center of the figure, I meant, and K is referred to as the keel of the ship, that is the bottom of the ship. And you can see B here. So if this is the water level here, this line here is the water level, right? This is the water level again of a ship vessel. So you can see that this is the water level of the ship. So you can see that the height from the water level to the keel of the ship becomes the draft of the ship. And because this part under the water level is the submerged part, that becomes the underwater volume of a ship. And the geometric center of the underwater volume, you can see, is the how you will put B there, it's the center of buoyancy. That's how you denote the center of buoyancy. And this I'm talking about is the box shaped vessel. I'll talk about the ship shaped vessel very soon. Alright, so that's KB. So K from so B is distance from keel, or K is referred as KB. It is the center of buoyancy is also referred from its distance from the aft perpendicular. In that case is called AB. And today we will not talk about AB, we will talk about it in my future videos. And finally, from the midship, if you talk about its distance from the center of buoyancy, it's called HB. And today we will not talk about HB and AB. I will focus only on KB, and in my future videos with further examples of numericals, I will talk about HB and AB. Today, if you understand KB, that's good enough, and that's the focus of the lecture. So if I go back to the 2 figures above, so KB of a box shaped vessel is half the draft of the vessel when the vessel is upright and on even keel, which you can see in the figure here. So the draft of the vessel is the distance from the keel to the water level, and B being in the geometric center of this box-shaped vessel when the vessel is upright and on even keel. So it's not listing, it's not tilting, it's not heeling. That is the kb of a box-shaped vessel then becomes half the draft. So half of the draft in this case here. But kb of a ship-shaped vessel, which is the next figure here, the second figure, the ship-shaped vessel, as you can see I've marked it here, it's a little bit more than half the draft that you can see here. So if half the draft was somewhere here, B is just above, maybe by 5 or 10% more than the half the draft. Alright, so with a ship-shaped vessel, because the underwater volume and the shape of the underwater volume changes in comparison to a box-shaped vessel, the center of buoyancy lies maybe 5 or 10% above the half of the draft. We'll put all this knowledge in the numericals below. Finally, for a triangular shaped vessel, as you can see here, the triangular shaped vessel, the KB or B, or the center of buoyancy, if K is here, will be about 2/3 of the draft. So you can see this is the draft, this is the water level. So I will put water level here. So whenever I draw this line, this is like a water level. So from the keel of the ship to the water level is the draft. So in a triangular shaped vessel, 2/3 of the draft gives you the center of the buoyancy, the position of the center of the buoyancy. Now let's talk about the first question. So the first question says that it's a box-shaped vessel and the displacement of the box-shaped vessel is 1640 tons and the dimension of the vessel is 50 meters long, 10 meters wide and 8 meters high. Find her KB in seawater. SW is seawater if she is on even keel and upright. So it's a pretty straightforward question. I have told you before that a box-shaped vessel when even keel and upright, the center of buoyancy will be exactly half the draft. So all we have to do is basically find the draft. If we know the draft, we know that half of the draft will be the position of the center of buoyancy. So let's see if we can find the draft from the information given to us, because the draft is not given to us in the question. So what is given to us is displacement. So W stands for displacement. Now displacement equals underwater volume by density. If this is the first video you are watching in the series of ship stability, I'll advise you to start from the very first video, because all there I have discussed the formula for calculating displacement and what is displacement and all that. So in case you don't know these terms, start from the very first video. That would be my recommendation. Alright, so displacement equals underwater volume of the vessel multiplied by density. Displacement is given to us as 1640. The underwater volume is always length by breadth by draft. Alright, it's not by height, it's by length by breadth by draft when you're talking about underwater volume, because the draft indicates the underwater volume's height. Otherwise the height indicates the whole height of the vessel. So the underwater volume will be 50 by 10 by draft multiplied by 1.025, because we are in density of seawater or salt water. Then take the unknowns on one side and take the knowns on the one side. So 50, 10 and 1.025 will go on to the other side. Therefore draft will be equal to 1640 divided by 50 by 10 by 1.025, which will give you 3.2 meters of draft. Now we know the draft, and KB of a box-shaped vessel is equal to half of draft. That's why KB will be half by 3.2, which is equal to 1.6 meters. So this is a pretty straightforward question. So whenever you see that the question discusses a box-shaped vessel and you have to find the center of the buoyancy, you know that exactly half the draft will be the center of the buoyancy. So all you have to do is figure out how to find the draft. So the information given to you in the question will be enough. It will be a bit tricky maybe sometimes, but you will know that somehow you can find the draft through the information given to you in the question. Let's move on to the second question. The second question says, this time it's a triangular shaped vessel. So what I have tried to do in this video is I try to take different examples so that you learn how to handle different examples, and that's why this time I have taken a triangular shaped vessel which is floating in seawater again. So seawater density is 1.025. Her water plane is a rectangle. That means the area which is submerged of this triangular vessel underwater is a rectangle. 40 meter by 12 meter. That's the dimensions, length by width. If her center of buoyancy is 3.6 meters, find her displacement. Alright, so now this time the center of buoyancy is given to you. When the center of buoyancy is given to you, and you know that a triangular shaped vessel, the center of buoyancy is located about 2/3 of the draft, as I showed above, you know you can find the draft. You have the draft, you have the length and width of a water plane, which is a rectangular, you have the density, you have to find the displacement. Okay, so let's start. So if you know the formulas, and I hope that your examiner gives you the formulas in the exam. If they don't, then you have to just memorize these formulas. If you know the formulas, always remember, write down the formulas of the item that you have to find. So in this case, if you have to find a displacement, you can do one thing, is you can write down the formula of calculating displacement, and then try to figure out what is given to you and what is it that you have to find out displacement, and that will guide you to solve the question. So anyhow, let's start with this question here. In this question, what is given to you is KB, that is the center of buoyancy is given to you from its keel, or distance from its keel is 3.6 meters. It's a triangular shaped vessel, so I know that the 2/3 of the draft is equal to KB. KB is equal to 3.6 meters, but draft is not given to me. But because KB is given to me, I can find out the draft. So that's why 2/3 of the draft will be equal to 3.6, which is equal to KB. Keep the draft on one side because it's unknown, and take the knowns to the other side. So take 3 here and 2 comes down here. So draft becomes 3.6 multiplied by 3 divided by 2, which is equal to 5.4 meters. You have found the draft now. Alright, so you have to now find the underwater volume, because the density of seawater is known to you. So all you have to do is find out the underwater volume multiplied by density, and then you will find the displacement. So if you can visualize this vessel here, and please pardon my terrible drawing, I am not very good in drawing, as you can see, but I have tried to display. So this is the water level here of a triangular shape with a rectangular water plane area. Alright, so this is the water level, and of course this becomes the draft, because the distance from the keel to the water level is the draft. Right, so this becomes 5.4 meters in this case, now that you have found it out. Now the water plane of a triangular shape, now this, because of the water, it forms this triangular water plane area. So you have to find the triangular water plane area, and then you can just multiply it with the length of the vessel going this way to find the volume of the underwater volume. The underwater volume, sorry. So area of triangle ADE, which is the water plane area, will be equal to half by base into height. This is because this is how you find the area of a triangle. The area of a triangle is equal to half by base by height. So if you see, the base is DE in this case, which is about 12 meters. You know why it's 12 meters, right? Because it's given to you in the question. The width of the vessel is 12 meters. So this is the width of the vessel. You can see from the drawing. So the width of the vessel, this width here is about 12 meters in this case. That's the width of the water plane area. Sorry, not the width of the vessel, the width of the water plane area. Alright, and that's why it's 12 meters, because otherwise the base is different from the DE here. So BC is different from DE. So the water plane area width is 12 meters. So anyhow, so you find out the area of the triangle by half base by height. Half base by height means half of the draft by the width of the water plane area, and which is half by 12 by 5.4, and which gives you 32.4 meters square is the area of the water plane, or the triangular water plane. But that's the area. You need to find out the underwater volume. So to find out the underwater volume, you will just take the area here and then multiply it by the length of the vessel. Length, because that is also the length of the water plane area. So you take 32.4 multiplied by 40, you get 1296 meters cube, because whenever it's volume it's meter cube, whenever it's area it's meter square. So displacement, which is denoted by W, equals to underwater volume by density. You have found out the underwater volume and you multiply it by the density, you will get the displacement, which is denoted in tons. So T stands for tons. Alright, finally I'll take the last question, and again this is a different kind of a question. So hopefully I have handled enough variety of questions so that if you get similar questions, you know what to do. The principle or the working out will remain the same, except the values will change and some words will change here and there, right? So the final question today is that you have a cylindrical drum. So like I said before, I'm trying to take different examples and different shapes of vessels. So the first one was box shape, the second one was triangular, and third one is a cylindrical drum. And the drum's diameter is about 0.8 meters and its height is 1.5 meters and the drum weighs 10 kilograms. Alright, 490 kilograms of steel is put in it, such that it floats with its axis vertical in fresh water. This time it's fresh water. Fresh water density is 1. Alright, that's a relative density. So you have a drum of 0.8 meter diameter, 1.5 meter height, and the drum weighs 10 kilograms. You have put 490 kilograms of steel in it, such that it's still floating with its axis vertical in fresh water. Find its kb. You have to find its center of buoyancy from the height, from the keel. And you have been given that pi is equal to 22/7. So you need value of pi to find the volume of the drum or area of the drum or anything. So pi is a, I'm sure you know about it, but pi is a figure which has a value of 22.7, 22/7. Alright, so let's start with the solution here. So the diameter of drum is given to you, 0.8 meters. Radius of the drum in this case then becomes half of the diameter. So this is half of the diameter is the radius. I'll show you what I mean below figure. So you see here in this figure, cylindrical drum, this is the diameter, 0.8. Half of the diameter, which is the radius, this is 0.4. Alright, then you have the height of the drum as 1.5 meters given to you. You can see here it's 1.5. The weight of the drum was 10 kilograms and you have put weight of steel of 490 kilograms in the drum. So you can see here all this is the steel, maybe steel pellets or something. It's 490 kilograms and the relative density of the fresh water is of course 1. So this all is given to you in the question. You can decipher from the information given to you in the question, and you have drawn a kind of a figure and to visualize what's going on here, right? And you can see this is of course the water level. So let's start with the solution here. So now that the weight of the drum was 10 kilograms and once you add 490 kilograms of steel in it, the total weight, and assume this to be a vessel, becomes 500 kilograms. Alright, so although this is not a vessel, what this basically teaches you is what to do if this was a vessel. Alright, so the same principle remains the same. So you've got the total weight of the cylindrical drum as 500 kilograms. What you can go from there is that so that also becomes the displacement. So displacement, because displacement equals the weight of the water displaced, and the weight of the water displaced will be equal to the weight of the object. So in this case the weight of the object is 500 kilograms, so therefore our displacement becomes 500 and the underwater volume and density displacement equals underwater volume by density that you have seen before in the example. So you will put displacements as 500 kilograms, but we don't use kilograms in displacement, we use tons. That's why you will convert the 500 kilograms into tons. So this is converting kilograms into tons. So therefore 500 by 1000 becomes the displacement, because 1 ton equals 1000 kilograms. Right, and this is what you are doing. You are converting kilograms into tons here. So 500 kilograms will be 500 by 1000, and you know that displacement equals underwater volume by density. You know the density and you know the displacement, so you take this figure here and divide it, you will get the underwater volume. So the underwater volume becomes 0.5, which is basically 500 by 1000, because 1 has no impact on the volume here or the figure here. So you now know that the underwater volume of the drum, that is the volume of the submerged part of the drum, can be found out by pi r square by draft. So normally the volume of the cylinder is found by pi r square by height. So if I had to find out the volume of the whole cylinder, I would say pi r square, that is pi is 22/7, r is 0.4 square, by the height, which is 1.5. but I don't want to find out the whole volume of the cylinder. I only want to find out the volume of the underwater volume. The draft has to come into consideration here. So the underwater volume of the cylinder will be found out by pi r square by height of the water, which is the draft. Alright, so we are always concerned with the underwater volume, underwater area, water plane areas, because that is the part that concerns us. Because once the ship or a vessel gets submerged in the water, that is the part we are concerned about. Because above that we have enough buoyancy for flotation, but it's only under that that becomes a bit tricky, because now it's submerged in the water and the gravity starts to act and starts to submerge the vessel further. So that's why we are only concerned with the underwater volume. So underwater volume is 0.5, you have calculated above, but it is also found by the formula pi r square, where this is pi, this is r, and because it's r square, so again r by the draft of the vessel. The draft of the cylinder is what you don't know, the rest you know. So therefore draft becomes equal to 0.5, and you take the knowns all to one side. So these ones come down here. Multiplication becomes division and division becomes multiplication, which gives you this equation here, and you found out the draft is 0.994 meters. Now you know that the center of the buoyancy can be found by half of the draft. Half of draft is center of buoyancy. Therefore draft by 2, which is 0.994 by 2, gives you the center of the buoyancy, or the height of the center of the buoyancy from the keel, which in this case becomes 0.497 meters. Alright, so I hope that this video was helpful for you to understand the concept of the center of the buoyancy of a ship. I have tried to take different examples, different shapes, and if you encounter any question with these shapes of a vessel, I hope that you will be able to solve these questions. If you have any doubts, or if you didn't understand something, or if you face problems in the future, please send me the question, the specific question, and I can work it out and put out a video for you. A question without examples is difficult for me to explain. So I have few students who ask me concepts, but they don't give me specific examples with figures. So if you give me specific examples with the figures, you give me a question that you have not been able to solve, I'll try to solve it for you and put a video out. Alright, and thank you very much for all the people who have subscribed and who are following me, who give me feedback. I really appreciate it. A few of my videos have had some audio issues in the past, and I apologize for that. I'm trying to work on that audio issue. I had no idea that issue was happening, so I'm trying to work it out, and that's why my videos are coming a bit late now. I'm trying to work out that audio issue. Once I resolve it, I hope to put out more videos. I'll see you soon with my next video. Bye, and all the best.